Log on, tune in, find out. Another good idea from Cambridge.
Fellner from Cambridge, and he's going to speak about aggregation pattern due to repulsive aggregating interaction potentials.
Thanks very much for the introduction. Thanks very much for inviting me. Thanks very much for everybody who is still here Friday afternoon after a very interesting, very long conference. I'll do my best to do things as entertaining as possible, and I also apologize for the people who've seen, like a few times the thing which I'm going to tell in the beginning, but since this was a problem which beat my intuition so many times, it's probably quite interesting for somebody to check it out again. Okay, so it's mostly joint work with Gail, who is also here and presenting the conference, and was inspired by a lot of discussions with Christian and with Marco and so forth. So what's the thing I want to talk about? It's sort of a Fokker-Planck type equation. What sort of processes are involved? There are three terms in this sort of equation which I have here. The first term would be some sort of diffusion. If you take the identity for A, then it's a quadratic diffusion. If you take logarithm, then it's a linear diffusion term. Okay? I'm mostly not going to consider diffusion. This is just there to give the background. The second term is the stuff which I'm really interested. That's an interaction potential, right? So I feel you, you feel me in a symmetric way somehow. And the last thing would be a confining potential which I can add if I have the urge to keep things together. The particles don't run away to infinity, which I would like to avoid. So I'm always going to have things on a compact support. And okay, one of the basic properties is that this Fokker-Planck equation conserves masses. It's written here. So I don't lose a particle, so I don't have birth on something or whatever. However, it's a very general model, right? It comes up in many, many different applications, and I want sort of just to line out a few of them. Like if you ask Giuseppe Toscani, for instance, he will tell you such an interaction potential can pop up in the modeling of inelastic material, for instance, okay? And what you see actually there is that, well, it has a certain form, and it usually typically leads to aggregation towards sort of measure type solutions within finite time, okay? Now you can turn on diffusion in order to avoid that if you don't like it, but okay, that's what it is. Another big class of potentials, interaction potentials, which are sort of in the background, are all sort of swarming collective behavior potentials, like Morse type potentials. Leonard-Jones for physicists or whatever, something like that. But in particular, I want to point out we've heard a lot about Keller-Siegel, and also if I would write a 2D version of the whole thing, I take the logarithm of interaction potential and I take linear diffusion. Here, what I essentially have a formulation of the elliptic parabolic Keller-Siegel model. And there we know very well that all of a sudden, despite having diffusion, sort of this singular interaction term can actually be so strong that it's more powerful than diffusion, and you will have still aggregation to Dirac measures, right? In 2D, there is a threshold phenomenon we've heard. We've heard that it depends on the initial mass. If you have too much mass in your system, you will aggregate to deltas. For little mass, there will be global smooth solutions. So in some way, this non-local term can be more powerful than diffusion, and that's why I want to focus on it. So I forget about diffusion for the moment. I'm interested in the dynamics of these interaction potentials and what does it mean for a population. And since I have to do with measure type solutions, which are usually very nasty, also numerically difficult to analyze, I try to do a trick. So I'm always going to consider the 1D case, and the trick goes back, for instance, to Leo Toscani, that you use the pseudo-inverse of your particles. So since mass is conserved, I just say it's a probability density, right? And then I can erase somewhere some space. And then what I can do essentially is, from the probability density, so I interpret rho as a probability density, I calculate the distribution function, and then I take the pseudo-inverse. It's essentially just flipping it around. And the pseudo-inverse has now a new variable, independent variable, which essentially corresponds to the mass before, so it goes between 0 and 1 somehow, limited by the mass. And then you can see, for instance, in the paper or by a previous paper by Marco and Martin Burger, that this sort of equation in 1D becomes sort of an integral equation with some confining part to it or whatever. So if you have seen that before, you know very well. If you don't have seen it before, it's not really important for you to understand what I'm going to tell. I'm just going to tell you this is much easier to do any sort of analysis on numerics with. So I'm going to do all of sort of the technical level on that sort of thing. To illustrate what I'm doing essentially here, you just think in that intuitive way up here. Okay. In particular, if there's no confining potential, so there is only this integral term with an interaction potential. This is, you know, you do get here the first derivative, right? So I said the interaction potential is symmetric. What I feel compared to you, you feel for me. So the first derivative is an odd function. And if it's an odd function, you immediately see, if you calculate the integral of this sort of new quantity, that this is conserved. So there's a conservation law we have to keep in mind. And it actually has a real physical meaning. If you go back to the density picture, this is the center of mass which is conserved, and I can just normalize it to 0, for instance, whatever you want. So this is a conservation law which I have to keep in mind, which is mostly the case. So I'm mostly interested in the dynamics of an equation and not so much in what it might model. But I want to point out one application which, for instance, Angela Stevens sort of directed a little bit. This would be sort of a directional model where you have alignment of some things in cell biology. And these things might be filaments, and they have some cross-linking proteins which essentially do the following. If these filaments try to be too parallel, they squeeze it apart. If they're sort of too far apart, they squeeze it back. So what you do get is some sort of a double well potential which decides about the angular distribution of these sort of things, these rods. And she sort of wrote an equation down which was very similar to that. There's a sort of a simplification of a kinetic model, right? And I just dropped the diffusion because that was also part of the game somehow. Anyway, I want to take this thing as a particular example, a double well potential, and I want to understand what sort of happens a little bit with that particular example of a double well potential. More specific, I'm actually going to be just taking two parameters of this function. It's essentially the curvature at 0 and where the minimum is. So in this extremal point, I just take the second derivatives and I call it alpha and beta. It's two values. That's the only two parameters of this double well I'm interested in. Okay. So there's a local maximum at 0 and a local minimum somewhere else. What you do immediately see with a double well, if you concentrate everything to one Dirac measure, that is formally a solution, but it's the solution which essentially is sitting on the unstable peak of the double well, therefore it's going to be unstable. Any perturbation will actually disperse it. So what sort of stationary states do you still have? And the intuitive thing is, of course, right. If you put two Diracs essentially somewhere, then you have a stationary state. The interesting part is there's not only one stationary state with two Diracs, that would be sort of two directions somehow, but there's a whole family. And essentially it depends on a sort of a parameter which you can interpret of how you distribute the mass between these two sort of Diracs. So that's my space. They have somewhere Dirac, they have a somewhere Dirac, and this has a certain mass. This has a certain mass, and the sum of the masses, of course, has to be 1. This is our normalization. But the way how I distribute the mass essentially depends on a continuous parameter, and I can do it whatever is wanted. I always get a stationary state. Well, it's a bit strange, right? Is it? There's a lot of stationary states. In some way, the problem is quite degenerate. Let's put it that way. Angela mentioned this, if you remember, this sort of mass selection principle, and there is not enough, let's say, sort of complication in the model going on that you really sort of decide where you go to. So that's why you have so many stationary states. Anyway, better to look at a picture. So what do you see here? This is sort of numerics. That's sort of the original measure value picture. So that is the physical space. And I start with something which is an approximation of 3 sort of aggregates, let's say. some smooth Diracs, okay? And this is my initial data, this bold line here, and I want to involve this according to a double well potential. Double well potential, take a very simple one, okay? X to the 4th minus x squared, something like this. Maybe I should draw a double well potential somewhere. Just something like that. So I let this involve, and numerically I always work on this pseudo-inverse picture, which you can read it, it's fine. If you don't matter about it. Essentially it means the 3 Diracs essentially correspond to this bold line here, the smoothed initial data. And everything where it's constant, more or less, means that you have lots of mass concentrated at one point. That's sort of the idea of the pseudo-inverse. And that's also where we do all the numerics. That's why it's so nice to calculate. But if we let it involve, actually what happens is, well, more and more aggregation happens with where there was already sort of a bit of an aggregate, right? So it moves a little bit, it steepens, and in the end what I do get is here I get a delta and here I get a delta as well. I can plot deltas, right? So essentially the real way to see it is that this is a straight line that merely means there is a delta, and this is a straight line that really means a delta, and they're separated by this sort of distance. That's what you represent here. So essentially this is a representation. It's not really what I numerically calculate. That's the real numerical picture. Okay? So you see that I'd like to see maybe something with more aggregates, but I fall back into a system with 2 Diracs. Beautiful. However, as I said, there are many of them, and for different initial data, I might have actually an equal mass distribution or an uneven one. Okay, so and observe both of these cases numerically. So somehow there must be a stability there, right? So you do some sort of trivial linear stability analysis. So that would be the linearized operator around such a 2 Dirac stationary state. So there is sort of, depending on where you separate the mass, there's 2 different functional expressions, and there are some parameters involved, and these parameters sort of combine these 2 parameters ahead of my double well. Okay, so remember I had somewhere the second derivative here and somewhere the second derivative here, and one of them I called alpha, and I probably called this alpha, and this I think I called beta. So they were the only 2 parameters I really cared about. And I have now 2 values here in this sort of linearization, which are essentially a convex combination of alpha and beta according to this mass separation parameter. So if I draw somewhere alpha here and beta here, or so whatever, maybe the other way around, I get here these lines lambda 1, lambda 2. Essentially, if you do the linear stability analysis, you make an exponential ansatz, you plug it into the equation, you try to solve things, you find 2 sort of eigenspaces which are very important for the linear stability analysis. The first one is essentially trying to shift things a little bit. So it would be, just try to follow my words, it would be that you take the position of this a little bit away and this a little bit away, and you do it so that the center of mass is conserved. So the shift has to be proportional to the mass of that Dirac. So you're allowed to do that, but with the double well potential, luckily we see that with the alpha, which is sort of convex, all of these sort of perturbation are actually stable ones which are going to fade away. So this is essentially the effect of the confining of my double well for particles which are separate for a certain distance. These sort of wiggles are always going to decay. And there's another eigenspace which is important to recognize. That would be if I take a particle as one of these Diracs and essentially I threw it into pieces. I take the same mass, but I sort of distribute it maybe in a smooth way, maybe I'll separate it in several Diracs, whatever. All sort of perturbations which do this independently, they're also sort of an important eigenspace. And they are stable under a very particular condition. They are stable exactly then when sort of literally the beta is essentially smaller than the alpha. So in a more interpretational way if the repulsiveness locally at 0 is sort of controlled by the attraction, by the confinement you get from alpha. Okay? So if the aggregation controls the repulsion, then all of this sort of trying to separate the Dirac into something is actually also not going to happen, and a perturbation like this is going to fade away, and you get again a nice Dirac. Okay? So I called this reallocations in my very bad English. Anyway, so what we do get in this case where beta is smaller than alpha, so I have the control of the repulsion, I get essentially always an open interval of possible mass distributions which are stable. So this is my mass distribution parameter. In case this is smaller, I have a full interval where it's stable, but if I try to distribute the mass too asymmetrically, then it's going to be unstable. Okay? So let me see what that means. Essentially, numerically, a little bit of a test. I can make some formal bifurcation analysis to see what happens if I touch sort of the border of stability, like the convergence to 2 Diracs we have seen before. We had that before. So this was certainly an example where I converged to 2 Diracs. So this is somewhere lying in that stable regime. But here I'm sort of just on the outside of the unstable regime. I help the scheme a little bit. I split the larger mass essentially into a little one and a larger Dirac. That would be more clearly here. So this is the larger Dirac, this straight line is the smaller Dirac, and this is the other Dirac on the other side. So I have 3 Diracs now, and I'm going to wait what happens. And indeed, for a long time, nothing really happens. And then after a while, I see a fast transition of this Dirac to the other one. So I've exchanged some mass. All of a sudden, I fall back into this interval of stability, and these 2 Diracs are completely happily stable forever. So what do we can say about, general steady states, right? First of all, why have I been talking about Diracs? Because actually, if you have a very smooth interaction potential, if it's analytic, you can show that the only possible stationary states are finite sum of Dirac masses. Okay? So for analytic ones, it's essentially, in order to have a stationary state, you do have a finite mass sum of Diracs, otherwise it's not possible. Unfortunately, if you essentially it has to do that this analytic function having can't have infinite many zeros. So for all of these Diracs, there is a function which is analytic, which should have a 0, and it can't be 0 everywhere, so therefore it only can have finitely many zeros. Anyway, if you drop the analyticity, it's not so clear really, and there are some more there are some counterexamples, but generally you could say the following. At least if you have a C2 potential, if there would be a sum of Diracs which accumulate to some point, then this sort of stationary state can't have a spectral gap. So it can't be really linearly stable in that sense. So therefore, it's probably not the most interesting in a physical sense to check stationary states of this. But otherwise, if you once have a certain sum of Dirac's a stationary state, you plug it into your equation, you come up with a condition. This is just a matrix condition which you can calculate in order to check if it's a stationary state or not. Unfortunately, it's not very instructive essentially, but it's trivial. You have to check it. In particular, you can come up with a stationary state which consists of 3 Diracs. And what it essentially does, when the 2 Diracs had the mass sitting essentially here and here, the 3 Diracs essentially will have one mass here, one has here, and the other mass here. So relatively speaking, and the dynamics of the 3 distances to each other cancels it perfectly. That's why it still can be a stationary state. So that wasn't so clear actually that you always can have that, but there's actually a way to really prove it for a double well potential, that you always will find that in the particular case where there's no confining potential. So, okay, the existence of such a stationary state doesn't say too much, but what you really want to know is if this is possibly stable or not. So we essentially do a stability analysis for this thing, and it's working again with these two eigenspaces I've mentioned you before, and they come up with two sort of conditions. The first one is a sort of a vector condition where you have a vector of quantities which you need to calculate, whatever it is, forget about the formula, which tell you if you have satisfied stability with respect to that you sort of tore one of the Diracs apart. So you have now n Diracs, so therefore you get n sort of conditions in order to guarantee you have stability with respect to this tearing a Dirac apart. Another type of stability which you need to guarantee is essentially this shifting the Diracs in their position, and this is a matrix condition you get. And if, you know, like that sort of has the right sort of spectrum, then you get also this linear stability. So there are, like in this example before, there are sort of only two type of eigenspaces which sort of govern the linear stability analysis, and this is how what to check, right? It's not more, it's just conditions you need to check. Anyway, given that linear stability conditions, you can even prove local nonlinear stability in a sort of Wasserstein L-infinity sense. If you don't know, if you haven't heard about Wasserstein L-infinity, don't worry too much. It would involve the infinity norm of this pseudo-inverse, but there is sort of more general ways to define it. Otherwise, don't worry about it too much. There is a certain way of saying there's a local nonlinear stabilities once you have linear stability conditions satisfied. You can actually pull that up into higher dimensions, I think, using some atomization principle, which is in the paper for Carrillo, Di Francesco, Figalli, Laurent, Slepchev. Okay, so now we have stability conditions, but I mean, is that 3 Dirac case, for instance, relevant? I can't really calculate it now. I mean, I could, but how many stable Diracs can I see? So let me do a little example. What I'm going to show you as a confining potential is sort of x squared, so this is sort of a convex confining thing that brings everything together, minus a smoothed version of the modulus. So that little hump here, that repulsive hump here is essentially something which should be a straight line up to here, and then there is an epsilon interval, so that's the whole space is 2 epsilon, where I smooth it in some way. I actually don't care about the precise smoothing. All I say is that the smoothing essentially has a vertical derivative at 0. So okay, this is sort of taking into account the symmetry respect anyway, is continuous and behaves essentially like a normal smoothing. That's all I need. And before I do any calculation, I just show you the pictures. So here I have a numerics for the double well potential with a rather not very smooth modulus, right? You see epsilon is 0.4, so this is really pretty round what you have here, not very edgy at all. And I start with initial data here, which is sort of 4 aggregates, let it evolve, and I fall back to what I used to see before, 2 aggregates, 2 Diracs. But if I turn the smoothing down a little bit, if I make epsilon smaller, start with 4 aggregates, I end up with 4 aggregates. So I really have a case now, an explicit example if you want, where 4 Diracs are stable, really stable, and I can show that. Now, funny enough, for the very same potential, if I start with different initial data, I end up with only 3 stable stationary states. So there's a non-uniqueness of a second kind. I showed you the stationary states here. There was sort of a whole family attached to it, to the mass distribution. But it's not the only non-uniqueness of stationary states you have in the game. Essentially, this shows you that for the same potential, different initial data converge to different stable stationary states. Okay? So it's not clear, essentially, if the potential would like to sustain 3 or 4 aggregates. And if you make it even smaller, you get many aggregates, right? So you start with 3 and then in the end up about 20. In particular, that's not so surprising because there is some formal heuristics you could do. If you have a local repulsion, that would be this thing here, that hump here, which you turn to a Dirac, then formally you essentially create a quadratic diffusion term in the equation which makes things smooth. So the more singular you get around here, there should be some sort of a smoothing effect introduced in the whole dynamics. And that's essentially what you saw in this example. In a weak way, more and more Diracs are going to converge to a limiting case. The limiting case is where you really have the modulus. And for this one, you can actually do an explicit calculation that your stationary state is something like the characteristic function between -1/2 and 1/2. So I have a situation where for that potential, in the limit I get sort of a continuous mass distribution on a certain characteristic interval, and for a smoothed version, I get many Diracs approximating that thing. And the preciser I do the approximation, the more I get of them. So if you heard the talk of Tatmo when he said local repulsion is very important, but it's too complicated, now you know why it's so complicated. But essentially, it's a very strange way of approximating things. Anyway, so you can make this example explicit. You can make an explicit example for the potential that for any number you give me, I can construct you a stable stationary state with that many Diracs. From a simple double well potential, which is just getting more and more like a modulus here. And you can do that with Klingel. Anyway, instead of taking too much analysis, I just want to show you more pictures, because it's surprising how rich the dynamics of that little thing gets. So here, for instance, is I take as interaction potential just minus the modulus, but I play with the confining potential. And let's make that sort of a double well potential. So I have now sort of a smoothing effect coming from that singular interaction potential, and I have a double well potential. And the stationary state, what I do get is essentially two continuous parts which are separated by a forbidden region, which is according to where the sort of the double well external potential is healthy or not. Let's put it that way. This is just fun. You can even numerically calculate what happens if in higher singular interaction potentials. That's sort of relevant to the theory, because that's actually, we have no idea how to prove theory for that for the moment. If you start with measure valued things, but otherwise everything behaves like you want it. In particular, what sort of you find if you talk about singular repulsive potentials, so now we have things which essentially have a modulus here. There's one very famous example, it's the Morse potential. That's very much used in all sort of swarming applications and so forth. It essentially is two exponential decaying functions where on a certain condition on the parameters, which you don't need to know precisely, but under these conditions, it essentially looks like that. So there you have a spike, and then it goes like this, sort of. I'm not very good in drawing exponential, but this is sort of the potential you have. Anyway, so that's the interaction potential, and it should behave sort of quite similarly. So let's see what's going on. Actually, this is already one slide too far. I just wanted to be here. So I'm doing some numerics again. Okay. I start with a uniform mass distribution in a certain interval between -3 and 3. So this is the support of my initial data. It's compact. It will remain compact. What you first see, so this is uniform mass, that's not going to be stable. They are developing aggregates. And after a certain while, what you actually find, there are going to be 3 aggregates, this dashed line. But these 3 aggregates are not the stable stationary state. Actually, if you wait for long enough time, they're going to collapse to one aggregate, which is sitting at the center of mass 10n. And what you see here probably is actually sort of the time evolution of the energy which governs that evolution. First, you converge to 3 aggregates, then for a long time nothing really happens, then you have a transition to this final aggregate, and this is really the stationary state. Okay? Quite fun. What happens if we increase the initial support a little bit further, right? So I just made it slightly larger from -3.5 to 3.5, just a little bit larger. What you see essentially, the basic behavior is the same. So this uniform mass distribution, the beginning, that slump of mass, starts to aggregate. There you have aggregates. They are now not Diracs, they're really aggregates. So sort of this singularity here prevents the formation of Diracs, but they're aggregates. And first of all, you see 4 of them, and then you wait again for a while, and then two of them collapse, and you end up with two stationary states, and that's really stable. That's again what you see here in the energy. What you see essentially is for the energy doesn't really change for a long time, then a fast transition, and then you're in the stationary state. This, for instance, would be the L2 norm for the solution, indicating there's still development going on until essentially you reach really the stationary state. And you can keep on playing that game. You can make the uniform, the support initially larger. Sorry, I haven't plotted here. But essentially what it means is you form first aggregates, in that case 6, and they keep on collapsing, and I have 3 aggregates as stationary state. Okay? So this is something we would very much like to understand, but it has similarities, so you can, you can think about a lot of things. It has similarities to what, for instance, was observed by Christian and Yasmin Tolak in a paper about Keller-Siegel, is that you form aggregates, and then you have a very slow dynamics for them to merge to each other somehow. And finally, if they come close enough out of these aggregates, they will merge to each other, and it's sort of a slow, fast dynamics. And you see it essentially here in this plot. So you form aggregates, that's more or less happens here. They have 6, then the outer 2 will merge together, then you have 4, and then finally you end up with 3. You can even play a little bit more nasty games with sort of double well potential. This is sort of now, you could say, a bit of a sort of a toy version of all of these sort of things. This is just like linear line, okay? So I have a certain repulsive area, and then I have attractive one. So if I do this sort of numerics, I end up with one lump of mass, and I'm happy. So you think, probably, okay, everything plays very locally somehow. Maybe it doesn't matter too much if I just brutally cut off, like my external potential far out, just set it to 0 essentially. But if you will do that, and your initial support of the mass is large enough, you end up with a very different picture. So all of a sudden, instead of converging to 1, I find, let's say, all of these lumps. And the length scale between of them is essentially set by the cutoff. So this is for all people which try to cut off this interaction potential at some point. If you do it ever, be careful. It depends essentially on the initial support of the data, if it is allowed or not. If you start with something which is close to 1 aggregate, you can always cut it off, it doesn't matter. If you start with something you don't know about the initial support, essentially, it might produce very different pictures. You can even make some more funny games to see sort of more interesting patterns. It's when you give sort of this double well potential different slopes. So I give the confining one a weaker slope than the repulsive one. So that's this sort of formula here. I introduce a lambda parameter which says that the slope here is just 1/2 than the one from the repulsive area. Then I do converge to an aggregate, but the aggregate itself has an internal structure according to the range of the repulsiveness. Essentially, it's torn apart into something which is sort of 3 finer aggregates. So it's 3 aggregates forming 1 lump of mass. And if you're not careful with the cutoff again, and your initial size is too large, you end up with 6 times 3 aggregates forming 1 thing. So that's, that's already pretty complicated to get some stupid little double well potentials, right? A lot of length scales involved. If you look carefully, actually you see that sometimes the numerics, the very primitive numerics I'm doing here, is already not completely trustworthy. Yeah, okay. That is actually just to support what I said before. Here it's just 1/3 of the initial support, and that's still enough to form 2 of these sort of aggregate lumps. And if I would decrease the size of the initial support less and less, it would just be 1 of these sort of structures. And that would correspond to the case where essentially it's non-cutoff. So it would never feel the cutoff in this sort of case. The initial support is not long enough. But so what you can do in order to convince yourself how robust are these, is this sort of a matter of the continuous modeling, is this bad numerics or whatever. So I was very lucky to meet some people which have more experience in doing some sort of lattice walk models. So this is some people in Melbourne essentially, and there they have being there, sort of currently still testing lots of sort of lattice walks model, which essentially should approximate somehow the continuous model, right? So what you see here is essentially integer number, so that's now my space is integer, and you hop to the left or to the right, and you have a certain amount of agents which do that according to these double well potentials in a discrete version of the very same problem. And if you do that, for instance, that this is the case without cutoff, you again get the very same sort of behavior. So there's now a randomness associated to it, because essentially you always choose certain random things. So it's a type of random walk which produces the same behavior. So that's reassuring in terms of that it really has a meaning what we see there. And if you introduce the cutoff, you still get the same, qualitatively same picture. So all of these aggregates outside of the cutoff area essentially, so that would be a potential which you brutally cut off again, and you haven't been careful with that. And you do get sort of these aggregates which hold this fine structure. And you realize that in all sort of stochastic random walk approximations, and that would be corresponding to the last picture. Okay. So what can we say analytically about all of these singular type potentials? Unfortunately, a little bit less than before. What you can clearly say, if you have a singularity at 0, so we are talking about double well potential, which again something like that. If you have a singularity at 0, that is here, which is attractive, so that would be the other way around, we again get a similar sort of stability criterion like before, with including local nonlinear stability, without going into details. If it's repulsive, then we only can handle a case which is essentially convex away from this singularity. So it wouldn't really cover the Morse potential yet. Maybe we'll find a way to do that, maybe not. Anyway, so to round the things off, I want to add a little bit diffusion, right? So far I've promised you that the interaction potential is the one which governs the dynamic, and that diffusion can be neglected as long as it's small enough. Here's the proof for that. So I'm adding in a numerical way, which is not 100% precise according to Professor Sturm, but okay, in reality, according to Professor Sturm, I add a little bit of diffusion. And what you do see, I'm repeating the case where I had this non-uniqueness of the number of aggregates. Remember, I had this double well potential which, according to the initial data, had either 3 aggregates, and in the other case 4 aggregates. And adding small enough diffusion, I still see the same picture. So diffusion doesn't change this non-uniqueness. Adding diffusion means I have either 3 smoothed aggregates or 4 smoothed aggregates, right? Diffusion allows essentially to select the mass between this non-uniqueness of the family of stationary state in some way, but it doesn't erase the non-uniqueness in terms of how many aggregates do I get from some initial data. So just to see that a little bit, that would be a simulation which should have 8 aggregates from initial data, right? And for very small diffusion, you find that. For a little bit larger diffusion, the time evolution already is important, and you find the stationary stage only 7 aggregates. The middle 2 somehow have merged to one march. I mean, this is, I've plotted here borderline case, which you just could believe it's 7. If I would have done a little bit less diffusion, it's more clear. It's just the borderline in order to indicate what happens if I put the diffusion too much. If I have too much diffusion, all of the fine structure is lost, and I end up with a huge lump of mass. That's what we really expect then, right? But it means that no matter how many aggregates my local interaction potential gives me, for small enough diffusion, I will preserve the structure in a sort of smooth way. So that's already where I'm going to stop. Don't let your tricks solve by double well potential. They look very nice, but just that they have 2 lumps doesn't mean that 2 Diracs is always the solution. There can arbitrarily be many stables. And if you get singular, actually, you introduce some sort of a diffusive effect, which is far away from a real diffusion, right? I mean, to get the real diffusion, essentially, you would need to have here Dirac, but still smooth things. And maybe that's relevant, maybe not.
Very much for this very nice talk. Questions? Martin?
I'm a bit confused about the first case where you have always these 2 deltas, and is there some bound? Can it be arbitrarily closed? if you have two delta,
Yeah.
can they get arbitrarily close?
No, there is sort of I mean, the distance between is essentially distance between here and here in the double well potential.
Okay.
Okay? If you add more and more Dirac, so if you approximate the modulus here, then essentially the spatial gap between the deltas is essentially of order epsilon. But it's not quite unique. It's just, let's say, there's an estimate we can do that is of order epsilon, essentially.
But also, if they are not very non-symmetric, it's still. Because I thought in the simulations, when you have symmetric, it was distance 1, and then you made it more asymmetric and take it.
Yeah, but the asymmetric is only stable until a certain point, and then it collapses.
But there is a ground state which is 1 delta probably, which is unique.
But no, this is always unstable, right? As soon as a double well potential, if you put everything at one point, it's always unstable.
What is the ground state? What is the energy minimizer?
That's a tricky question. All of this continuum of two Diracs have actually different energy.
Yeah.
But the dynamic stops before you could reach the minimizer.
Yeah, but
Only if you add a little bit of diffusion, then the one where you distribute the mass symmetrically is the energy minimizer.
don't they have this? I mean, the energy derivative is 0 for all these. So they must have this.
No, it's not.
Then they are not ground states.
Yeah, but
They are not stationary
yeah.
states, I mean.
Yeah, no, they are not ground states, but they're stationary states because there is nothing anymore to dissipate further. The dissipation stops.
In an infinite-dimensional space, some strange thing happens.
It's a very strange thing. Okay, I have to understand it
You
better.
have continuums of steady states
Yeah.
with a slope of energy, but the gradient is zero everywhere.
This is what I'm complete. Okay.
So yeah, so the energy essentially of all of this is a parabola, and if you distribute the mass symmetrically, then you have the minimum of the parabola. But nevertheless, essentially, if you don't have diffusion, if you only have the interaction potential, you can converge to something which is not the minimum, but then you don't have anything anymore in the dynamics to dissipate further the energy. Because the energy dissipation at that point, which is not minimum, is already 0. Only if you would add a little bit of diffusion, you have some new dynamics, which slowly lets you converge to the energy minimizer. And that's then when you, in the case of two Diracs, distribute the mass symmetrically. However, you can still have stable stationary states with many Diracs, and then it's still not essentially unique if you approximate 3 or 4 Diracs or whatever. So it's quite complicated.
Chemotaxis problem we did. It's the same in the chemotaxis problem we did. You have many plateaus. If you only look at the hyperbolic problem, all these are stable.
Yeah, but there I have the rho times 1 minus rho, which stops the dynamics. He doesn't have that. I mean, at rho infinity, the dynamics is not stopped in that way. But anyway, I have to understand that in detail. I think it's too much.
Sorry, it was too much.
Okay. Are there more questions? Okay, so let's thank Klemens once again.